All right. So last time we talked about the architecture for information retrieval. So usually you will need to build an index, right, before the query arrives, and so you can answer the query immediately in a short time by using those index instead of scan through the documents. Okay. So we said no to build this index. It's a kind of a big data problem because you have to scan through the documents and do some analytics in order to build the index. And once the index is built, usually it can load it into some online system like database, so you can response the query in a shorter response time. Okay. So we mentioned for especially for documents, people use the back of words representation because it's simple and it's usually fit our needs for searching, right? So people are already used to use keywords for searching those documents. But it's not just the word, right? You have to, um, determine the importance of those words so that your search will be more, uh, closer of match to the user query. Okay, so we mentioned those words need to also require some pre-processing, right? And all those steps are also suitable for using a system like MapReduce because you can see it's also just some very simple data preprocessing, right? It also read out the data and try to do the tokenized normalization, etc. All those could be applied for the for the for the token you read out from the documents, right? So all those things should be able to process independently and in parallel with the help of a system like MapReduce. Okay, but of course, more importantly is how could we build an index? And for a search engine, or for this case, usually people usually use the inverted index. So that is the index we're going to introduce you and explain how they could be implemented using MapReduce. Okay? And before we get into the inverted index, first we can talk about some more basic indexing strategy. And it's also the way you build the index also depends on how you would like to retrieve the data, right? And so one of the way to retrieve or search data is using the Boolean retrieval. So it means that the user will describe some conditions in their expression, right? And the data will either fit to the description or not. So it's a it's a Boolean expression, right? If it match, we should retrieve all of them, and if it doesn't match, then it shouldn't be returned at all. Okay, so this is what we call the Boolean retrieval. Okay? This type of query usually doesn't fit the search engine too well because of um, first of all, you might have too many data satisfy your query, so you have to retrieve a bundle of data, and it might be more than the user needs. Secondly, and more importantly, is there is no quality to the one that match to your query, right? You cannot tell which data probably closer to your query because they are either no match or it doesn't match. We don't know how close it is to our query. So there's no way to prioritize them or order the results. So no, as you today, right, when you use the search engine, it's actually a form of a rank retrieval. So that means the result retrieved from your query are ranked, right? So they are prioritized. And of course, the user expect the one that's closer to his query should rank higher and show first, right? So the search engine also need to sort it the result according to the query and the content of the documents. Okay, so that's what we mean by ranked retrieval. Okay, all right. So with this way to retrieve, then first of all, right, the user can see the content he wants to see at the first place. Also, for the search engine, that means it doesn't actually need to retrieve everything, right? He only needs to try to retrieve the most closely related results first and show it on your screen. And it can search the rest of the document later on when you click next on your screen, right? So there's some time you can delay for searching. Even and also you can even have a constraint, right? A limits so that you can stop searching at some point without actually retrieving all the contents. Okay, so that's why it's actually a preferred way for both the user and the system. Okay? However, the challenge here is how could you rank the content? And it should rank by the relevance to the query, right? So the question becomes how you estimate the relevance between the query and the document. So of course there are many models, right, and so many theory, different approach to do that. And one of them is called the closeness of vector. Okay, so the idea is that you can represent the query and the document by a vector, right? And each dimension you can see you can represent by n dimensions, a vector with n dimensions, and each dimension represent is a word, right? And in the simplest form, this is actually a binary vector, means that the value of each along each dimension is either 1 or 0. 1 means the document or the query contain that word or term, and 0 means it doesn't. Okay, so it depends on how many words you have, then that's the length of your dimensions. Okay, and in this simple form, assuming we just have two words, then you can visualize it on a two-dimensional space, right? And the idea of closeness means that it defines the similarity between the query and the document by the angle between the two vectors. Okay, and the angle, if the angle is smaller, means they are closer, right? For example, if you can see that D here means document, and you have several documents, right? So here we have D1, D2, and so on and so forth. And also we have the vector for Q, that's your query. Okay, so imagine if D and Q are the same, then their value for each along each dimension will be the same as well. So their angle will be 0, right? On the other hand, if the vector is the angle between the vectors are larger, then it's an indication that the value between two vectors are more far away, right? So that means they have less similarity. Okay? So one way to quantize the similarity is using the vector. Okay. All right. Specifically, if you want to calculate the similarity by the vector, uh, then basically we are calculating the cosine value of that angle, right? And this is probably what you have learned from high school, right? So if we represent it by the value of, along each dimension, then this is what the equation should looks like when we try to calculate the cosine value between vector D and the vector Q, right? And since this is too complicated, so usually we try to simplify it by only leave the the upper part, right? So that's this part. Okay. So to simplify the representation, we can calculate the angle or the degree of similarity based on their weight value along each dimension. Okay? All right. And so this value, if it's smaller, means they are, more similar. And if the value is larger, that means they are less similar. So we can use this value to rank the D, right, associated with or respect to the query Q. Okay. Okay. However, this representation is quite simple because, as I said, the value for W is either 0 or 1. So it doesn't show the importance of the term in that document or respect to that query, right? Imagine maybe a document have the same term, many, many times, then the importance of that term should be more for the document because you can represent that document more, right? On the other hand, if another word it only show up once in the document, then the importance of that term to that document should be less. So we can further generalize it to represent the weight as the importance of the term respect to that document. Okay, so therefore, actually, this is the foundation of the first Google search engine. So they proposed this strategy to adjust the weight of the term with respect to query, so that the query result will be more accurate. Okay, and idea is that they think the weight should be measured by two directions or two aspects. The first one is the importance is a local factor, right? The local factor is what I mentioned. It's try to measure how important is the term with respect to the document. Okay, so if a document has more number of the term, then that term should be more representative in that document. So the weight, as you can imagine, should be higher, right? On the other hand, you can also measure the importance by the global aspect, means that how many documents has that term, right? If that term show up in every document, then the importance of that term should be less, right? Because everyone has the term, so uh, probably it has less. It is less meaningful, right? On the other hand, if this term only show up in one document or very few amount of documents, then the importance of that document should be higher. Okay? So that's the intuition behind how we could decide the term, uh, the value of or importance of a term respect to a query or a documents. Okay, all right. So to reflect that, then the intuition becomes that if a term appears very often in a document, then then we should assign a higher weight, right? So the term should proportional to the frequency of that term in a document. On the other hand, if a term appears in many documents, then we should assign a lower weight. So that means the importance of the term should be an inverse proportion to the number of documents with the term. Okay. All right. So the first one, the local aspect, is what we call the term frequency. Okay, so that's the term frequency, the frequency of the term in a document. And the global aspect becomes the inverse document frequency. So the importance is the inverse of the frequency of the term in all the documents. So it is a importance respect to all the documents. So it's from a global view. Okay. All right. So with that to intuition, so people propose this what we call the TF-IDF term weighting strategy. Okay, it's pretty long, but it's a short name for what we mentioned, right? TF is the term frequency. IDF is the short name for inverse document frequency. So basically, this is a weighting strategy that combine the two factors together. Okay, so as you can see over here, um, the weight now of ij means that this is the turn I uh, respect to document j. Okay, so you can see the weight of a turn actually will be different respect to each document. Okay, the same term, but its importance could be determined by his document. Okay, so I is the term and J is the document. Okay, so TFIJ is what we said, the term frequency, right? The frequency of turn I in document J. So we say the weight should be proportional to term frequency. So that's why you can see this is what we have here. They are proportional, right? And on the other hand, for document frequency, right, is the frequency of the turn respect to all the documents. So for example, if you have 1,000 documents and 10 of the documents has this turn, then the value of DF should be 10, right? Because 10 document has this term. And we want to normalize it. So N, you can see, is the number of documents. So in our example, N should be 1,000 and DFI should be 10. So that means 1 out of 100 document has this term, right? And if this value is smaller, actually should be more important. So that's why you can see the DF is actually at the bottom, right? So this value, if it's smaller, then this term will be larger. Okay. Okay. And also because we want to normalize it or bounded the value, so you can see we take the log out of this term. Okay, so it will not goes to a number with unlimited values. Okay, so it's just a way to try to normalize this term, and we multiply those together, so that will satisfy our intuition that the weight at the end will proportional to the term frequency and inverse proportional to the document frequency, right? Okay. So this is the general form. And of course, in practice, people usually will add many other maybe coefficient or tuning parameter to adjust this equation. But this is the basic form of TF-IDF. Okay? And as you can see, try to capture two concepts, right? In terms of the importance of term frequency. Okay? All right. So as the result, right, still, if the value is higher, that means the query should be should be more, get a larger value out of this correlation. And so it can be ranked higher in the search results. Okay. So in order to build this inverted index, okay, why is called the inverted index? First of all, because you can see the form of an inverted index means that the key should be your term, and your or you can say a row is a term, right? And the column is a document. Okay, so we basically try to build an index that try to record what are the documents that contain a term. Because when user try to query the document, the query only contains term. So with that term, you can look up this table and to find out what are the document contain that term, right? And then you can calculate the angle of the vector to get our ranking results, right? So it's called the inverted index because the index is built with respect to the term, not respect to the document. So that's the inverse direction of your documents. Okay. All right. So before we show how to calculate the angle, the relevance, first of all, of course, you have to be able to derive this value, right? You have to build an index, and the index should contain enough information so you are able to compute the weight of a term respect to a certain document and certain query. Okay? So you can see that equation, right? Depends on the value of term frequency and document frequency. So in this inverted index, not only we will record what are the documents that store this term or contain this term. We also need to keep the information that can represent the term frequency and the document frequency. Okay? So what happened is this is the index we would like to build. Okay. So in this example, you can see we have 4 documents. Okay. Each document contains some terms or words, right? And the result you can see, for example, blue, right? Blue only show up in document 2. So you can see over here. So we have a value of 1, means that the blue there's showed up once in document 2. On the other hand, for fish, you can see it appear in document 1 twice, right? Also document 2 twice. So we would like to store 2, right? For document 1 and 2. Okay. So this exactly, as you can see, those values represent the term frequency, right? The term, how many, the occurrence of a term in a document. Okay? And for document frequency, we would like to remember how many documents contain that word. So you can see this is the result, right? For fish, it show up in 2 documents. So the document frequency should be 2. Okay. All right. So you can see this is after we scan through the documents, then we should able to do some simple statistics and aggregation, then generate this inverted index. Okay. And of course, this is to store this index in this form is very consume lots of space because or waste a lot of space because there are many empty entry in this array, right? So a better way to store those information should be like the right hand side. Usually we will use a linked list, right, to store the necessary information, right? So because we don't know how many term frequencies are there for each term, but we do know there's only 1 document frequency value. So we will store the document frequency first, and then followed by a list of term frequency, right? So it depends on how many documents you have, right? Then the linked list can keep growing. Okay? So you can see in this way, we will only use the space for storing the necessary information. Okay? All right. So so this is the general form of inverted index. So the next thing is we would like to show you how we could implement a MapReduce program, right? That can scan through the documents and output this inverted index file. So we can use it to answer query online. Okay? All right, so I believe you still remember the workflow or the programming model of MapReduce. And it turns out it's quite easy to implement the inverted index algorithm in MapReduce because it pretty much to the programming model, right? So the idea is that for the map function, supposedly it should scan through the document, right? And whenever he sees a term, he will emit the term and the document ID, right? The document number and the term, how many times it sees in the document, right? And if you only read part of the document, you can still just output the partial result. It doesn't matter because in the reduce phase, we're going to aggregate all the count together. Okay, right? And for the real search engine, usually they also emit other information associated with any term he find from the document. For example, like the term position, right? Which paragraph or which line did this term appear in this document? So those information usually showed up in your search result web page as well. So for user to select probably which document is he want to actually look into. Okay. And for the reduce, as I said, it simply try to gather all the the key value pair from the map face, and then collect them and write it out like the linked list we mentioned above, okay, in the previous page. Okay. So let's just look at this animation, then you can have a clear idea how it works. Okay. So again, this is the input, right, of our problem, and the map function, as I said, you can imagine, for example, each map function will scan one document, right? And so for the mapper one, he will generate one, two, and fish, okay? And whenever he sees, he can do some local aggregation. So for example, here he can just output fish appeared in document one and appeared it twice, right? And also find one from document one once, etc. Okay. So say you have a lot of documents and you can launch many mappers, depends on how large your data set is, then how many, right? You will generate a proportional number of mappers to do the parallel processing, right? And you will generate all those intermediate key value pairs. Okay. All right. So you can see this is already the term frequency we need for our inverted index, right? But we haven't generated the document frequency yet. Okay. So for the reduce function, of course, after going through the shuffle and the grouping steps, then what we should expect is we will aggregate the result by term. Okay, so you can see the term should be the key for the intermediate result. So according to the map reduce programming model, then all the the records with the same key should be grouped together and send it to the reducer. Okay, so in this case, for example, maybe cat, fish, one, and red, all four keys are sent it to reducer one to do the aggregation. So so actually it will call the reduce function 4 times, right? Each reduce function for each key. Okay, and the reduce function simply try to concatenate, right? Concatenate the key value pairs of that term together to generate our inverted index content, right? So like this case, fish, right? It appears from document one and document two, but they will be aggregated together and generated emit from a single reduce function like this. Okay, and of course I didn't show, but the reduce function can easily count the document frequency, right? By just output the length of the values received for a key. So in this case, the document frequency should be 2, right? Okay, so that's it. So you can see this is a very simple map reduce program. but it can process enormous or unbounded amount of data to build the inverted index for those documents. So this is exactly how Google built their first generation no search engine. Okay. All right. So some more detail. Okay. So although yes, we can implement the MapReduce code in that way, but in order to accelerate the query process, usually there's a few more things we need to pay attention to, right? First of all is this list should be sorted, right? Why it should be sorted? Because for query, we want to know whether it showed up in a certain document. If this list is sorted, then we can use binary search or other way to quickly identify whether a document contain that term or not. Okay. Secondly, usually, so that's why this term usually is sorted as showing over here. You can see this case, we try to append all the results and we try to sort this linked list by their document ID, okay? So that we can accelerate the query process. However, this implementation is not scalable in the MapReduce framework. The reason is, in order to, you can see P, right? P is a memory variable, right? It's a variable in our memory. So if you want to sort P, then that means all the contents of P also need to store in the memory, so we can apply those sorting library code. But imagine if we have millions of documents, then this linked list can be very, very long, right? And also, we mentioned in practice, usually they not only store this term frequency, sometimes they will store some posting. Posting means some additional information like the paragraph number or the line number we mentioned, those metadata or description for that term. So the memory size you need to store a single term probably costs several bytes as well, and you might have a very long linked list. So it will become impractical to store the whole linked list in the memory. Okay, because you may have this out of memory problem, right? Supposedly this code should be run across millions of documents. So if you want to sort it in the memory, then you may encounter the OOM problem. Okay, so this is a straightforward way to implement the inverted index, but actually we need to implement it in a smarter way, that we would like the framework to sort the result for us, so that we don't need to keep those all those values in the memory. Okay, how to do that? The technique is called the secondary key. Okay, so what it means that we not only want to sort the records by their key. For each key, we also want to sort its values by some of the content in the value, okay, such as the document ID in this case, right? The way to do that is, as you can see over here, originally, this is the definition of key values from the map function, right? Remember, the key is just the fish, the term, and the rest of the content are stored as a value, okay? But in order to sort our records by the value, we will actually move or duplicate the value to the key. So you have a composition key in this case. right? As showing here, you have fish and maybe -1 and fish -9, something like that. Okay. So with this, remember the MapReduce framework automatically will sort all the keys by their by all the records by their key, right? So he will automatically sort those records at not only the fish but also the part of the value. Okay, and if they sort together, then when they aggregate, become a list for the reduce function, when they do the grouping, then he will also grouping by this order. So that means, for example, here, all those records are for fish, right? And after the sorting phase, it's guaranteed those records will be ordered in this way. Okay, so after aggregating this way, and then we do the grouping, then we are guaranteed the fish one will be the first record in the list, followed by this record and this record and this record. Okay, so we can sort it by both, right? The composition key, but when we do the grouping, we only group by the first part of the composition key. So they will send it to the send reducer, and when they send it, it will already order by their values. Okay. All right. So we later on we have more example to show you. Okay, but basically the key is that uh, don't do sorting on your own in the MapReduce framework, because you have to consider the memory is always limited. The amount of records you have to process, even for a reduce function, could be unlimited. So your code should only handle one record at a time or one value at a time. If you want to do the sorting, you should leverage the framework to do the sorting for you, because the MapReduce sorting is on the disk. It's no, it's scalable. It doesn't rely on abundant. It's implemented on abundant memory. Okay, so it's not limited by the size of the data size. Okay, all right. So we'll have more example to show. So you have know exactly what I mentioned here. But the key is this code doesn't work if you really process on large data. And the way to do that is sometimes you have to use this technique to leverage how the sorting and the grouping is done by the framework. So the key value, after you do this, then the list of P, send it to the reducer, should already be sorted. Okay, it is sorted in the sorting phase, not sorted within your reduce function. Okay. All right. So we will leave it at that, and we will show more example later on. Okay. So anyway, you can see this is how we could build an inverted index using the MapReduce framework. And after we do that, as I said, in order to do the query to compute the similarity with respect to a given query, that shouldn't be done by MapReduce, because evaluating the query should be done at real time, and it's not fit for MapReduce, because MapReduce is a batch processing, it's not stream processing. Okay, so as we mentioned, the index you build should be stored in some other online system like database, and then the query will simply scan through that inverted index and to calculate the equation we mentioned before. Okay, so that should be very fast, because first of all, the calculation only involve the row that contain the term in the query, right? For example, if your query, for example here, if your query doesn't have fish, or if your query only have fish, right? If your query only has fish, then all you need to do is to process this line, right? to compute the cosine value. Okay. And also you can see the evaluation is a random access. It's not sequential read, or it's not a sequential read. So it's another reason this index shouldn't be stored on a file system like HDFS, because Hadoop file system prefers sequential read and append, not random read. But for query, you need random access, random read, and you only need to read a part of the content, and you have to do it online. So if you implement the implementation on MapReduce, the performance should be pretty bad and much slower than the database. So the query side should not be done by MapReduce. Okay, only the indexing part is done by MapReduce, like we mentioned here. Okay. All right. Okay. So that's it for MapReduce. We will give you a few more content about the API for MapReduce and a few more example in the next lecture. So for now, I think it's enough that you should have an idea what is MapReduce and what kind of application, a real application, can be built by MapReduce. Okay. So the last part is we will introduce other payroll processing framework or solution in the Hadoop ecosystem. And they are both quite well known. One is called Spark. The other is called Hive and Pig. So Hive and Pig is actually a SQL language, a SQL-like language built on top of Hadoop. And Spark is an in-memory processing system that borrow many concepts from the MapReduce framework, but they implemented, but different from MapReduce. Spark store the data in the memory, while MapReduce store the data in the distributed file system. Okay. All right. So why we have those new tools? Because of the trend we mentioned, and we will also explain a bit more later on. Okay. All right. So let's have a 10 minutes break. Then we will wrap up this lecture.